CS1010X Lecture 10, Implementing Data Structures.
Right, and let me just recap on what you should already know. All right, so basically we have learned some simple Python statements. Define, you build functions with that, return a value for a function. Lambda creates a new function. Right, if, and else. This is the control structure, conditionals. And then you have the loops for the iteration, for, while, break, and continue. And then you need to import basically libraries. Okay, and then we taught you two different primitives for data abstraction, tuples and lists. So tuple is an immutable structure, list is a mutable structure, but they are quite similar. So it turns out that at this point you have pretty much finished the class. Well, everything that you have learned is pretty much what this class is meant to teach. So why are we teaching some more? Well, it turns out that from now forward, right, what we're doing is that we will be essentially doing examples, right? So the things that you've learned, we'll show you how to use these elements, right, to do more complex things. It's not really new stuff per se. There's just new ways of applying old stuff. So if you remember from first few lectures where we were working with the what you call a picture language, right? Those pictures and you had the situation whereby you have many different kinds of functions, but essentially they're all based on two things, right? The turn left or turn right, okay, and also the stack frag, right? So with turn left or turn right, either one of them will do. And stack frag, you can actually define many things, right? So similarly, what you have learned so far is pretty much the full repository of all the Python stuff that you need. And moving forward, what we're doing is that we're just showing you examples on how to apply these things. Part of it is to expose you to new concepts on how we think as computer scientists. The other part is to give you more practice and examples in how we can actually use these basic tools. Alright, so now we'll come to today's main agenda, where we will use a game and we'll show you how we can apply some concepts of data abstraction, right, in building the data structures for a game. This game is called a game of NIM. And then we'll talk a bit more about how we can design and implement data structures, and also how for one data structure you can have different implementations. Right, so that's the agenda. Alright, I'm not sure how many of you are familiar with this game called a game of NIM, but it's very simple. There are two players, right, and the board consists of piles of coins and or maybe sticks, right? Some people play with sticks, and the idea is that you remove some number of coins from one pile, right, and any number as long as you don't go beyond that pile. And the idea is that the player takes the last coin, or if you play with sticks, the last sticks is the one that wins. All right, let's take a look at an example and let's see how it works. All right, so let's run. Okay. So this is the game of NIM. So there are two piles of coins, there's pile 1 and pile 2, and you're asked which pile will you remove from. I can try pile number 1, I can remove 2 coins. Right, and the computer removes 1 coin from pile 1, then I'll remove from pile 1 2 coins. Okay, I'll now remove from pile 2, remove 3 coins. Whoops, sorry, I lost. Right, because the computer now removes 1 coin, and I'm lost because the one removes the last coin wins. Right, so let's try again. So let's say I start. Right, and now I remove 5 from the first pile, and then I remove 4 from the second pile, and now I win. Now to implement this game, you need to do a few things. So first, you need to keep track of the game state, right? You need to know how many piles of coins there are, and how many coins are there in each pile. You need to specify the rules. You need to figure out how to play this game, and finally to glue everything together. But let's see how we write a simple game of this kind where we deal with only 2 piles. Now in general, you can have n piles of coins. That's something that you can do later by yourself. Now let's take a look at for the game state. Okay, what do we need to keep track of? Well, obviously you need to keep track of the coins. Right. Now, if you remember your midterm exam, we also had this Tower of Hanoi, right? And your job was to design the data structure that's required to keep track of the different disks in the packs, right? So similarly, what we do now is to keep track of the number of coins in each pile. Now, because the coins are kind of the same, so there's no need to keep track of any kind of order, right? So game state, wishful thinking, we assume that we have something that is called make game state, right? Where m and n are the number of coins, and essentially that gives us a game state. What else do we need? Okay, we need to know the size of the pile of coins, right? And so suppose you have two things, so the game state and your P. P is the pile number, right? And then this size of pile of coins will give us the number of coins. We can also remove coins, right? And N and P, we can remove N coins from a pile P in the game state, and this returns your new game state. And what else? Okay, so this is how we play the game, right? So this is the game. Okay, so you play, all right, and the game takes in the game state and the player. So the player can either be human or computer. Now you basically show the game state, right? Display the game state, right? And then after you show the game state, there are a few things, right? You check whether the game is over. Okay, if the game state is game over state, then you announce the winner, right? Very simple. Now, if the player is human, you ask the human for a move, right? And so it's actually this thing, you get a human to move, right? And then after that, you call play again, right? And now it becomes computer because it's the computer's turn. Now, if the player is computer, then you get a computer make a move, you let the human go next. Okay, so that's it. So this is essentially the game loop. So this piece of code is sufficient for us to play this game. Now, what happens if we evaluate this? Okay, well, Mickey Mouse is not a person, right? So, well, essentially we will do the following. We will basically add another error detection code, right, to make sure that everything's fine if the people don't follow instructions. Okay, now we'll go on to discuss how we implement the parts of the game, right? So this is wishful thinking, right? So earlier we just assumed that we can do all these things, and now we'll pick up the pieces. So first is displaying the game state. It's very simple. You have a new line. Pile 1 is, you get the size of the pile of 1, right? Pile 2 is the size of pile 2. Okay, so the two piles, and then this is that. Now, next, game over. How do we do? Okay, now is game over, right? Game state. Basically, you just check, whether the total size of the game state is 0. Once there's no coins, the game was over, right? What is the total size of the game state? Well, you just size of pile 1, right, plus the size of pile 2. Okay, so very simple again. Right, how do you announce winner? If the player is human, that means when it comes to the player's turn, there's no more coins, then it means the computer took the last coin, so you lose, okay, the player loses. And on the other hand, if the player is a computer where there's no coins left, then the human has won, so you win. Now, then how do you do a human move? Well, you just ask the human. So we have this code here, whereby first you ask which pile we remove from, and then we ask how many coins we remove, right? And we use this thing called prompt. Okay, so what's prompt do? Prompt essentially has this command called input, which will ask the user for an input, right? And the string is the message. So here will be the string, right? And essentially, after you ask the human for the pile, as well as the number of coins for the pile, you remove the coins, okay, from the game state. Now, why is it int here? Well, because N and P, they are strings, so we need to convert into int. Next, we talk about AI, how to play the game. Well, this is how we play the game. Okay, so pile is 1 if size of the game state 1 is bigger than 0, else is 2. Means you look at the first pile, if it's not empty, you pick it. So computer will remove 1 coin from pile string P, and essentially will remove 1 coin from the pile. Okay, now is this a good strategy? Okay, think about this. Now we go to the game state, right? So we have talked about how we assume the game state exists. So now we can see the following. Now let's say we can do make game state n m, which is 10 times n plus m. Okay. Now if we want to return the size of pile, game state pile number, if its pile number is 1, we will just essentially divide by 10. Okay, find the quotient. If it's not, we will return the remainder. Okay, so this is what? This is m. Sorry, this is n, and this is m. Alright, and to remove a coin from a pile, we just check. Right? If pile is 1, we just return 10 times the number of coins. If else, we just return 10, the game state minus number of coins. Okay, so what is the problem? Well, what's clear from this example is that your m, okay, is less than 10. So that means this particular representation is good enough if you have 5 points per pile. But once you have more than that, then life is hard, right? So let's look at another way. Okay, it's more kind of natural way. Basically, we can make game state nm and return nm. So this is a tuple, right? So the size of game state p is just p minus 1 because this is 0 and this is 1, right? Okay. Now, how to remove the coins? It's actually check the power number. Okay. And if it's 1, what you do is that you basically change the game state. Okay, basically you take the game state 1 minus num coins, okay, and it goes into the first pile, right? Similarly, if it's the second pile, then it goes into the second pile. So it's quite simple, right? This is exactly the same as the rational number example we saw before. All right, let's take a look at how we can modify name. Now, suppose you want to do undo. That means that the user did something and you have to undo something. So, and also in this new case, only human can undo, computer cannot undo. All right, and essentially we want to remove the effect of the previous move, right? So you will remove both the computer as well as the human move. So because what happens is that the human moves, then instantly the computer moves, and then it goes to the human again, right? So essentially we want to remove two moves, right? So human must enter 0, okay, to undo. So remember in the game, typically what happens is that the human gives the power number, and then after that you will choose the number of coins, right? So when you choose 0 power, you undo. So the key insight now is that we need to keep a data structure to remember the history of the game states. So how will you do this? Now, so before each human move, what we can do is we can add the game state to the history, right? And then what undo is actually you just take out the latest game state from the history, right? And make this current game state. All right, so to do this, we will use what we call a stack, right? A stack is what we call a LIFO structure. I think we've discussed what we call a queue, and actually we'll look at the stack again in class in a few weeks, I think. And LIFO means last in, first out. So basically, the guy, you think of it as in this picture, okay, it's something like a little container with a spring, right? So the stuff you put underneath, right, will go to the bottom, and then when you pop things out, you come from the top first. All right, so the items are removed in the reverse order from which they were added. Now, so we assume this. We assume that we have a stack, right? What we can do is that we can make a stack, okay? This gives you an empty stack, right? You can push an item S into the stack, right? And you can pop an item out from the stack, and you can check whether the stack is empty. So these are the operations that you can operate on the stack. In fact, we will do this again in class. Okay, so let's take a look. So let's say stack is S is mixed stack, right? You pop S, none, right? And if you push 5 into the stack, right? And then you push 3 into the stack, when you pop S, you get 3. You pop S, you get 5. Okay, you first get 3 and then you 5. So it's in the reverse order. And after you pop 3 and 5, obviously it's empty. Okay, and this is something you can do as homework. Now, so assume that we have already done that, right? Then we can do the following changes to name. Okay, that means that we can create a new object called game stack, right? And when you ask for the human move, okay, instead of just checking for what we did earlier, we add in this condition, right? We check for whether the stack is 0. If it's 0, that means we need to go and handle the undo, right? Otherwise, we'll first keep the current state in the stack, okay, and then we do what we did before. Okay. Now, how do we handle undo? So this is the quick overview. It's quite simple, right? So the old state, right, is actually this thing that is on top of the stack. So you pop it from the top of the stack, right? Now, if old state, what does this do? This checks whether or not this is null, right? If the stack is if there's nothing in the stack, then you read null, then this will be false, right? And then you go to no more previous move, and then you return the current move, right? If not, then what you do is you display the previous move, and then you will return the human move of the old state. That means you will ask for the human to move again. Okay, not sure how many of you have played this game online, but it's called 2048. Alright, so this comes to the end of the game on him. Right, I hope you found it interesting. But for your homework, you'll be actually doing this game called 2048. I'm not sure how many of you have wasted your life on this game, but you'll be doing homework and there'll be a little contest where you can write a little AI that basically solves this problem. Right, so it's very cool.